value.
Okay, sir.
Yeah, we can start now. Hai na?
Yes, sir. Sure, sir.
Yeah. Okay, I think screen is already shared, and so just let me just close SPSS files, and can you see the PPT? Is it visible? Is the PPT visible?
Yes, sir.
Yes, sir.
Okay, okay, okay. All right. So let's look into chi-square. Chi-square test is a non-parametric test, and with the help of chi-square test, I mean, it can be used for testing of goodness of it. Now, what do you mean by goodness of it? Goodness of it stands for that if there is a theoretical background, or theory says something, and you are doing your experiment, then your experiment matches with the theory or not. If it matches, then we say that fit is good. If it doesn't, then we say that it is not a good fit, right? And moreover, goodness of fit also refers to, let's say you are given some kind of data, and you want to check whether normal distribution fits well to this data or some other distribution fits well to this data. That is also taken care of by chi-square test of goodness of fit, right? So to determine whether a variable has a frequency distribution comparable to one expected, you will have this thing. So I'll take up one or two examples, then you will be more clear. Let me give you one or two examples of goodness of it. Now, if you are aware of, then Mendel has given theory that is called Mendel's theory, and Mendel has proposed the offsprings in the next generation. Listen to me carefully, please. If you don't know even anything about the biosciences or biological sciences, don't worry at all. It is just a theory given by Mendel. Mendel says that offsprings, I mean the generations which will come, the offsprings in the next generation are likely to be in the ratio of 9:3:3:1. What does this mean? That means if there are 1600 offsprings of some species, 900 will be of one type, 300 will be of one type, again 300 will be of another type, and 100 will be of another type. This is what we mean by the Mendel's law. 9:3:3:1. That means, or you can say if there are only 16, then 9 will be of one type, 3 will be another type, 3 will be of third type, and 1 will be one type. Or if there are 1600, then you can. So this is what the Mendel's theory is about the generation, next generation offsprings. Now you are conducting your experiment and you want to verify that theory, right? Now when you take 1600 species, and out of the 1600, let's say you are not getting 900, but you are getting 882 instead of 900. Then in the second case, you have to be 300, but you are not getting 300, you are getting 308. 308, right? In the third case, it has to be 300. Now you are getting 310. And in the last case, it has to be 100, and you are getting also 100. And total of yours will also be 1600. Total of Mendel's is also 1600, right? So Mendel says that it has to be in the ratio of 900, 300, 300, and 100. And your ratio is coming out to be 882, then 308, 310, and 100. Now, question is whether your experiment and Mendel's, what the Mendel say, according to his theory, whether your sample fits to that theory or not, whether your sample observation fits to that particular theory or not. So obviously, if there is a close resemblance between the two, if there is a close resemblance between the two, then it fits well to the Mendel's theory. But if there are a lot of differences, then your data doesn't fit well to the Mendel's theory. So that is, for that purpose, we use what is called chi-square goodness of fit test. Hopefully the example is clear. Yes, please. Is the example clear? Hello. Am I audible? Yeah. Okay. So how we test this kind of theoretical aspect? So here is observed frequency, here is expected frequencies. Observed frequencies are those which you observe, like 882, 308, 310, and expected you have 900, 300, 301, 100. That is your expected. This is what the expectation is. This is what you observe. So if there is a closeness between observed and expected, then fit will be good. But if there is a large differences, fit will not be good. So this is tested with the help of chi-square. So expected frequencies can be based on theory, previous experiment, comparison of groups. So that could be. So let's take example. So chi-square test of goodness of fit. Example. The average prognosis of the total hip replacement in relation to pain reduction in hip joint. Now, whenever there is a hip replacement, then after two years, 3 years, people are being asked about how was your experience. So this is the experience shared by the people. I mean, this is what the theory says. This is what the theory says because it is expected, and this is what you observe. That in 80% of the cases, people are generally have excellent result. 10% of the people are having good results, 5% medium, and 5% bad. So total is coming out to be 100. But in your case, when you observe that what happens when you have the 100 patients, what happens actually in your case? It says that 95% are excellent, good are only 2, medium are 2, and bad is only 1. The question is, this is at the large scale survey based result. This is what the theory says, that these are the likely results to be happen, and these are your results. So these are observed, these are expected, right? Now I will apply this formula. Summation, observed minus expected square divided by expected. So here is the result. So this is your expected 80, expected number 1 80, expected number 2 10, 5 and 5. From here I am writing, where 1 stands for excellent, 2 stands for good, 3 stands for medium, 4 stands for this. And in your results, observed is your 95, 2, 2 and 2. Now based on this, formula is with me. So this is the formula. How this formula will be computed? Very simple. So 80 minus 95. Square that quantity and divide by 80. That is the first figure. Plus 10 minus 2, square that quantity, divide by 10. Plus 5 minus 2, square that quantity, divide by 5. Plus 5 minus 1, square that quantity, divide by 5. This is what the formula says. Observed minus expected square, divide by expected, and take the sum. So there will be 4 sums that will give you the value of chi-square, and then there is a tabulated value of chi-square. So your chi-square degrees of freedom. How the degrees of freedom are computed? Degrees of freedom are computed because this is 2 rows and 2 columns. So if I write side by side, so 95 will be in front of 80, 2 will be in front of 10, 2 will be in front of 5, and 1 will be here. So you are having 2 columns and 4 rows. 4 row. So degrees of freedom is number of columns minus 1, number of rows minus 1. So you will be having chi-square with 3 degrees of freedom. And this is the value which you are getting, 14.2 after solving that all the 4 sums. And this is your chi-square. Chi-square value from the table is 10.83. And your computed value is greater than 10.83. So it will going into the rejection figure. And this, if you compute the p-value with the help of software, it will come out to be less than 0.001. So null hypothesis will be rejected. Null hypothesis will be rejected. So that means there is a, what is null hypothesis here? There is no discrepancy between theory and experiment. That means theory and experiment results are same. Alternative, there is a discrepancy between theory and experiment. So null hypothesis rejected. So your result is that there is discrepancy between theory and experiment. Maybe if you see from your eye, your results are better, in fact, right? So this is how you can compare what is called chi-square test of goodness of fit. Another aspect of chi-square test is to check the independence, of attributes. If two given attributes are given, then you can check whether they are independent or not. I'll give you example. Just wait for a moment. So chi-square test is usually used with R rows and C columns. Already explained to you. Then expected frequencies for any table can be computed, and the same formula can be computed to compute the value of chi-square. So let us look at this example. Now, locality, and this is gender, male and female. Now, somebody has counted how many males are there in rural area, how many males are there in urban area, how many females are there in rural area, how many females are there in urban area. And if you take a total on this side, row total will be 31, 45 plus 24 will be 69. And if you take the column total, it will be 40, because 24 plus 16, 45 plus 15 is again 60. And if you take the total of this and total of this, it has to be same. It is 100, right? Now, what is the problem? Problem here is, this is what we want to test. This is our hypothesis. Test the sex distribution is independent of locality. And alternative, sex distribution is dependent on locality. Now, what is the meaning of independence dependence? Sex distribution is independent of locality. That means distribution of male and female is almost equal in rural and urban. Distribution of male and female is almost equal in rural and urban. Then in that case, they will be independent. But if they are not independent, they are dependent. That means sex distribution depends upon locality. Then either there are more males or there are more females in rural or urban area. The distribution is not same. So hopefully you understand what I'm trying to say, right? Now it doesn't involve any parameter. Hypothesis does not involve any parameter, like mu is equal to mu naught, or mu1 is equal to mu2, or sigma 1 square equal to sigma 2 square, or p is equal to p naught, or p1 is equal to p2. Nothing is involved. It is simply a sentence. That's why chi-square test comes under non-parametric. Under non-parametric, there is no parameter. So you can recognize that this is a non-parametric test. And it can test independence of attributes. What are the two attributes here? One is gender, another is locality. So gender is independent of locality. You are testing under H0, and under alternative, they are dependent. Now, question is, how to get these are the observed frequencies. This is what you have observed. How to get the expected frequency? How to get the expected frequency is very simple. This is given in this formula. For any row and column, expected frequency is nothing but you look at the row total, multiply with the column total, divide by the overall total. For example, if I want to compute expected frequency of 15, then it will be row total 31, column total 60. So you multiply the two, 60 into 31, divide by 100. Similarly, if I want to compute expected of this, 45 का expected निकालना है, so this 69 into 60 divide by 100. 16 का निकालना है, 31 multiply by 40 divide by 100. 24, 69 into 40. So you will get all the expected frequencies by using this formula. Now you have observed frequencies, you have expected frequencies. Substitute in the formula, same formula, observed minus expected square, divide by expected, take the sum, and degree of freedom will be number of rows, number of column minus 1. So number of rows is 2, number of column is 2. So 2 minus 1 into 2 minus 1. So 1 degree of freedom. So if you do that, the calculation, these are expected frequencies. After doing the calculation, expected frequencies can be obtained. And once you have the expected frequencies, by multiply row with column total divide by 100. So you will get all the frequencies. And from there you apply this formula. Value of chi-square is coming out to be 2.52. And degree of freedom is 1. Because 2 rows and 2 columns. So 2 minus 1, 2 minus 1. And if you compute the p-value, your p-value will come out to be 0.134. 0.134 means your p-value is more than 0.05. More than 0.05. What is our null hypothesis? That the sex distribution or sex distribution is independent of locality. And it is accepted because p-value is more than 0.05. So you can say, yes, there is almost equal distribution of male and female in locality. So this is what do you mean by the chi-square test. Chi-square test does not involve any measurements. Let me just repeat, very important sentence. Chi-square test does not involve any measurement. Measurement means it is not like PG and UG score, or it is not like measurement like BMI or IQ levels. IQ level is a measurement. This is not a measurement, it is a counting. So when counting is involved, for example, how many males are in rural area, it is counting. How many males are in urban area, it is counting. How many females in rural and urban, it's counting. So whenever counting is involved, you cannot apply parametric test. And for counting, one of the important tests is chi-square test. Okay. So this is what do you mean by chi-square test. And so in 2 by 2 table, if one of the cell frequency is less than 5, then generally we compute it with the help of 8's correction, and we apply 8's correction. Otherwise, there is, if small frequencies are there, then you have to replace the chi-square method with Fisher's 8's correction or Fisher's exact test. Fisher's exact test, right? So I will show you how to apply, how to compute this in SPSS by using such type of example. So here is the practical example. Okay, let me take one of the data set. Okay, now there is a problem in eye, and that problem is called post glaucoma problem, जिसको हिंदी में बोलते हैं काला मोतिया. And people in the old age, they faced with the problem of glaucoma. Now, glaucoma in most of the cases depends upon the history, whether the parents are having or some relations are having, or maybe some ancestors like grandfather, grandmother, they are having glaucoma problem, right? Now, there are two variables. This is called history of glaucoma and this is called gender. I want to see whether gender is independent of history of glaucoma or not, or male female depends upon history of glaucoma. So here hypothesis will be, try to understand the problem. Male is 1, female is 2, and history of glaucoma, if it is history, if the history is present, 1, and if it is not, then it is 0, right? So from there you can construct a 2 by 2 table. From here you can construct a 2 by 2 table, and that will give you row and column. Row and column will be your column will be male and female. On this side you will get history of glaucoma, yes and no. So you will get 2 by 2 table. Similar table to this. Here you will get male and female same, and instead of this you will get actually history of glaucoma, yes or no, and you will get certain frequencies. And on that chi-square will be applied, and we can test that sex distribution is independent of history of glaucoma. If I prove the result that sex distribution is independent of history of glaucoma, whether you are a male or a female, it doesn't depend upon. But if I reject the hypothesis, yes, you can say either male are having more glaucoma problem if there is a history, or female are having more glaucoma problem, right? If it is not independent. So that will be the conclusion. So let's look into the result. So it's very simple to apply. Go to analysis. Please note down the steps. Go to analysis. Go to descriptive. And in descriptive, go to cross tab. Cross tab means crossing the two variables. Cross tab. In cross tab, it is asking what do you want in row. In row, we want gender. So take the gender here. In columns, we want history of glaucoma. History of glaucoma. This is history of glaucoma. And then click on to statistics. In statistics, there is chi-square. You click on to this chi-square. That's it. So chi-square value will give you p-value and compare it with alpha. Press continue and press OK. That's all. So you are getting the result. That is the table I was talking about. There are 212 observation. No observation is missing. So here is male history of glaucoma. It says it is present. History of glaucoma is present in 139 out of total 150. It is present in 139. Absent is only 11. In female, out of 62, it is present in 57. And this. And this is the p-value. Pearson's chi-square, this is the p-value. 0.855. Now 0.855, is it less than 0.05 or it is more than 0.05? Yes, please.
Greater than.
Greater than. So this is greater than. So your hypothesis will be rejected or accepted?
Accepted.
Accepted. भाई greater हो गया तो आप दिमाग में बिठा लीजिए बार बार, पंखा याद कर लीजिए. Reject H naught when P is less than alpha. Accept when it is greater. 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 I have repeated 3 times now. So it is greater, so accept it. So that means history of glaucoma doesn't depend upon whether a person is male or female. There is almost a equal distribution, right? Almost a equal distribution. That is the crux of this experiment. Yes, please. Is that okay? Hello?
Yes, sir.
So that is called chi-square test. So we have covered F test, we have covered T test, all the initial basics. Now I am moving on to the last topic, that is called discriminant analysis. Before moving on to discriminant analysis, if you want to ask any question, you are most welcome, please.
Sir, sir, excuse me, sir. Sir, after analysis, where I will go? Will you please show that step once again? After analysis?
You go to analysis, you go to descriptive. Under descriptive, there is a cross tab. You go to cross tab and then take your sex variable under row and history of glaucoma under column, and then go to statistics. In statistics, you click on to this chi-square and continue and press OK. You will get the result. So you are getting the result along with the 2x2 table.
Okay,
Is
sir.
this
Thank
okay?
you, sir. Okay, sir. Thank you, sir.
Any other question you want to ask, please? If you have any question, you are most welcome, please. Yes, please. No question?
No, sir.
Okay. इसका मतलब है आपको सब कुछ समझ आ रहा है. तो इसीलिए हमने एक शेर लिखा है आपके लिए कि मैं रास्तों पे चलता नहीं हूं, मैं रास्तों पे चलता नहीं हूं, जब मैं चलता हूं तो रास्ते खुद ब खुद बन जाते हैं, वो अपने आप ही बनते चले जाते हैं जब मैं चलना शुरू कर देता हूं. तो लगता है कि आपने चलना शुरू कर दिया है. और जब आदमी चलना शुरू कर देता है तो जिंदगी में कोई शिकवा शिकायत नहीं होती. शिकवा शिकायत तभी होती है जब वो एक जगह बैठ जाता है. जब पानी बहता रहता है तो उसमें काई नहीं जमती, लेकिन जब वो स्टेगनेंट होता है ना एक तालाब के अंदर तो काई जम जाती है. तो आपको चलते रहना जिंदगी में, रुकना नहीं है, रुकना नहीं है, राइट. और रुकने वाला इंसान हमेशा पीछे रह जाता है. इसीलिए हमने एक शेर लिखा था कि माना कि हालातों से इंसान बदलते हैं, माना कि हालातों से इंसान बदलते हैं, पर हालात भी हम इंसान बदल सकते हैं. हम ही बदल सकते हैं और कोई नहीं, राइट.
बहुत खूब सर, बहुत खूब.
जी. और जब आप चलना शुरू कर देते हैं, आपको कामयाबी मिलनी शुरू हो जाएगी, तो आपके दिल से जो आवाज निकलेगी वो ये कहेगी कि हर राहें आसान लगती हैं, हर राहें आसान लगती हैं, मुश्किल जो भी आए वो भी मुस्कान लगती हैं। जी, तो with this we are moving on to the last topic for today's session, that is discriminant analysis. Let me close all this. If you still have any question, you are most welcome, please. Okay. Let me go through the theory of discriminant analysis. Very, very important topic. Let me move on to the last topic. Okay, discriminant analysis. Discriminant analysis is an important technique to discriminate between two given populations or sometimes more than two given populations. Right? I can take up examples so that you can understand what do you mean by discriminant analysis. So let me go through certain basics of discriminant analysis and what are the statistics which you need to compute. So discriminant analysis, try to understand please, is a technique for analyzing data when criteria or dependent variable is categorical and the predictor or independent variables are interval in nature. So it is just like regression analysis. In regression analysis, we have y as a dependent variable, x1, x2, xk, they are independent variable. But here only distinction is, in case of discriminant analysis, your dependent variable will be going to be dichotomous. Dependent variable will be dichotomous. Dichotomous means it is present or it is absent, or it is male or female, or you can say it is professional or non-professional, something like that. But the independent variables are going to be continuous variable, like it depends upon number of factors, like x1 is a continuous variable, x2 is a continuous variable, xk is a continuous variable. All these are continuous variable. Only restriction in discriminant analysis is your dependent variable. Your dependent variable has to be dichotomous, right? Okay. So what are the objectives of the discriminant analysis? Development of discriminant function. We will develop one kind of discriminant function. I will tell you how to get it. What is a discriminant function? Let's say I'm dealing with 15 variables, x1, x2, x15, right? Then discriminant function is nothing but a linear combination of variables, linear combination of predictors or independent variables. What is a linear combination? Try to understand, please, those who are not from mathematics. Suppose there are two variables, x1 and x2. Then linear combination of x1 and x2 is denoted by L. So L will be equal to a1 x1 plus a2 x2, where a1 and a2 they are constant. Small a1 x1 plus small a2 x2. A1 and a2 they are constant. So this is called a linear combination of two variables. So if there are three variables, then your L will be a1 x1 plus a2 x2 plus a3 x3. So there will be three. There will be three variables. Similarly, if you are a 15 variables, so you can think of what is a linear combination. So L will be equal to a1 x1 plus a2 x2 plus right up to a15 x15. So this is called the linear combination. So it will develop some kind of linear function, which is nothing but a linear combination of independent variables, which can best discriminate between the categories. Between the category means present or absent, between male and female. So it can discriminate. That linear combination can discriminate between the set of categories. So examination of whether significant differences exist among the groups in terms of the predictor variables. Then out of, let's say there are 15 variables, out of 15, Suppose how many are important to discriminate between the two categories? Maybe 7 or 8, maybe 4 or 5, maybe all of them. So that can also be done with the help of discriminant analysis. So determination of the predictor variables contributions to the most of the interdifferences group. And you will also come to know that which variable is there, which is the most important to discriminate, which one is the next one, which one is the next one. Then at the end of this, you can also assign, because you will be getting some kind of discriminant function, you can assign a new individual. If some new person has come, so you can assign whether this will go to this group or this will go to this group. So discriminant analysis is also called a classification technique. Discriminant analysis is also called a classification technique. So I'll give you one example. If this theory you could not understand, then everything will be clear with the help of that example. Then evaluation of the accuracy of your classification, how accurate your results are. If some new individual have to be assigned, then what will be the accuracy level of your classification? Generally, if your accuracy level is more than 70 or 80%, it is considered to be a good classification model, right? That means if you want to assign 50 new individuals, whether this will go to this group or this group, out of that, if 40 or 45 are going to in the right direction, that means classification is good, right? Okay. Let's take one example, and that will give you a clear idea what is the meaning of discriminant analysis. Now, in India, after doing 10+2, there are two people either move to the professional courses, engineering, medical, or maybe management. So they are all professional streams. Or students move to the non-professional stream. They just do BA, MA, right, etc. So this is professional stream and this is non-professional stream. Now, if somebody approaches a psychologist, and the parents of the child approach a psychologist and ask what my child should do, whether he will go for the professional courses or he should go for the non-professional courses. Then these psychologists, they observe certain traits like mental age, IQ, communication skill, communication score, convolution score. So they study certain parameters, certain variables, which are there for the professionals, which are also there for the non-professionals. So what they initially do, they take a sample of, let's say, 500 people. Let's say out of the 300 are professional, 200 are non-professionals, and study all these traits, personality traits, skill development scores, IQ, mental age, all these. Let's say K different type of traits, X1, X2, X3, XK, right? Where X1 could be mental age, X1 could be mental age, X2 could be IQ, X3 maybe convolution score, X4 maybe skill, X5 may be communication, and so on. So you can understand what I'm trying to say. Now, based on this, now you have only two categories. This is your dependent variable. Your dependent variable is either a person is professional, let's say professional is 1, non-professional is 0. Okay. Then based on this, it looks into a linear combination of variables. This is a linear combination, B0 plus B1 X1, B2 X2, B3 X3, BK XK. And it develops what is called discriminant function. So this is a discriminant function. This is a discriminant function. Now these parameters actually, once you know X1, X2, let's say I have a data of 500 people. Out of that, 300 are professional, where in the first column I'll write 300 times 111 and 200 times below that 000. Then in the second column, I have all the values of X1 of the 500 people. Then in the third column, I have all the values of X2. And in the kth column, all the values of XK. So this is how the data will look like, right? And based on that data, now data is available, you will get this kind of equation. You will get this kind of equation, right? And once you get this kind of equation, This equation will give you discriminant score. DS stands for discriminant score. Now, you have the equation with you. Suppose some new individual has come and psychologists have noted down their mental age, their IQ, their convolution, and all these scores and substitute in this equation. Suppose there are 10 variables which are important. So x1 up to x10. So he had substituted. And this B0, B1, B3, they are estimated from the 500 observation. They are known to you from the given data. So given data of 5 observation, you can estimate these unknown coefficients, beta naught, B0, B1, B2. So only thing is, if I can provide the value of x1, x2, xk, you will get discriminant score. So once you get the discriminant score, after conducting the discriminant analysis, there will be two centroid. It will give you two centroid. The first centroid is called C1. That centroid will be for professional, and another centroid will be for non-professional. Now, based on this equation, you are going to compute DS. That is called discriminant score. So if your discriminant score is closer to C1, then you will ask the parents of the child that he should go for professional courses. But if his or her discriminant score is closer to C2, then you will ask her, then you will ask the parents that you should go for non-professional courses. So this is a classification technique where new individual can be classified based on the discriminant function and centroid or discriminant score. So this is the crux of the entire discriminant analysis. Yes, please. Is the problem clear? Hello? Or is there any doubt?
Yes,
We will
sir.
do it clear. We will do it practically. So basically, it is a classification technique. Whether a new individual will be opting for professional or opting for non-professional, you can decide depending upon certain parameters, right? And psychologists, they do very good job these days. And many of the parents, they always approach psychologists after 10+2. Which type of stream my child should take up so that he should not face difficulty. And they observe certain traits and characters, x1, x2, xk, and based on that, they develop the discriminant function score, and then they give the suggestion whether you should go for professional or non-professional, right? Okay. Now, have you gone through the ANOVA regression already? Have you gone through ANOVA, analysis of variance, or regression, multiple regression, simple regression? Have you gone through or not?
थियोरेटिकल हो गया है, hands on practice नहीं किया हुआ है.
अच्छा, चलिए कोई बात नहीं. So this slide is not important, much important. There are certain statistics which you need to understand before you conduct discriminant analysis. That what is the meaning, right? So there are certain important things. First, when your dependent variable is dichotomous, like professional or non-professional, like male or female, then this is called two-group discriminant analysis. But if there are three categories, professional, non-professional, semi-professional, then it becomes multiple discriminant analysis. But today we will focus only on two-group discriminant analysis. Now, how many discriminant functions you can try? Discriminant functions, if there are only your dependent variable is dichotomous, you will get only one discriminant function, DS. But if you have more than two categories in dependent variable, let's say 4 categories, then you can have up to 3 discriminant functions, DS1, DS2, DS3. If you are having 3 categories, you can have up to 2 discriminant functions. If there are G groups of categories, then G minus 1 is the number of discriminant functions which you are going to get. And the first function, let's say DS1, the first function always give you the highest ratio of between groups to within group sum of squares. The second one, which is uncorrelated with the first one, give the second highest ratio, and so on. So this is a discriminant analysis result. You will get discriminant score D. This is called discriminant score. These are discriminant coefficients. They will be available from the data, and these are called predictor or independent variables, right? Through which you want to predict whether I should go for the professional or non-professional. Now, how these coefficients are estimated? These coefficients are estimated with the help of a technique in statistics, which is generally called maximum likelihood estimators. So based on the maximum likelihood estimator, we compute these unknown coefficients. Okay. Then another statistics which will be associated with is statistics associated with discriminant analysis. You will get canonical correlation. Canonical correlation has to be high generally. You know correlation, Spearman's rank correlation, or Pearson's correlation coefficient, but canonical correlation is something different. What is a canonical correlation? Canonical correlation is nothing but correlation between discriminant score and groups. Correlation between discriminant score and groups. If groups are professional, non-professional, corresponding to that, there will be discriminant score, and you find out the correlation, that will give you canonical correlation. So it is a measure of association between single discriminant function and the set of dummy variables. Dummy variable means dichotomous variables. Centroid, I have already explained that you will get one centroid for one category, another centroid for another third category. Then you will get a classification matrix. And classification matrix is basically called prediction matrix. How many cases have been correctly classified? How many cases have been correctly classified? And what is the rate of misclassification? So that will also appear. If 70% and above classes are correctly classified, model is good. So there are some other statistics. For example, discriminant function coefficients, that B0, B1, BK, they are all discriminant function coefficients, and they are computed from the data. Discriminant score is nothing but multiplication of those coefficients with their x1, x2, xk. You multiply and get the discriminant score. Then one of the features that will appear for discriminant analysis is called eigenvalue. Because if there is a multiple discriminant, then there will be actually two discriminant functions, three discriminant function, ds1, ds2, ds3. Then which discriminant function is important? Generally, that discriminant function will be important whose eigenvalue is more. Whose eigenvalue is more. So eigenvalue is a very important concept. You must have used in factor analysis also. So only those factors are extracted in factor analysis whose eigenvalue is more than 1. Same thing in discriminant. Only those discriminant functions will be valid where eigenvalues are large. So you will get the eigenvalue also. Then basically out of, let's say, if there are 10 predictors, x1, x2, x10, out of that, maybe 5 are important, maybe 6 are important, maybe 4 are important. How will you come to know? So it will give you a type of ANOVA table. And in ANOVA table, actually, the particular variable like x1 will be taken as a dependent variable, and your professional, non-professional, which is categorical, is taken as a independent variable. And then ANOVA is run, one-way ANOVA. And it will give you that which variables can make a significant contribution to discriminate between the two groups and which cannot. So you can remove those which cannot discriminate, right? That is given by their F values and their significance. Then group means and group standard deviations. So you will get a table that if there are two groups, for each group there will be group means and group standard deviations. Then correlation matrix you will also get. Then the most important part is this one, that is called Wilks lambda. Now Wilks lambda is basically a test whether you can apply discriminant analysis or not. Its value lies between 0 and 1. And if the Wilks lambda value is coming out to be non-significant, then you can say that discriminant analysis technique is not applicable to your data. So it has to be significant. So in the analysis final output, you will get Wilks lambda value, and this Wilks lambda has to be p-value. You will get a p-value for Wilks lambda, and it has to be less than 0.05. If it is not, do not apply discriminant analysis to your data, right? So sometimes it's also Wilks lambda for each predictor is the ratio of within group sum of squares to the total sum of squares. Value lie between 0 and 1, and if its value is near 1, then it doesn't discriminate. If it is closer to 0, then it discriminates. Okay, that's all about certain statistics associated with discriminant analysis. Now we will do analysis by using some practical example. Now, if you have any question till now in discriminant analysis, please ask me before I start with the numerical example. Is there any question in discriminant analysis, or the technique is clear where to apply? Yes, please.
Clear, sir.
Clear. Okay. Now here is an important example. During the vacations, generally, people go for visits. For example, last year we went to Andaman and Nicobar. Sometimes people go to Kerala, sometimes Himachal Pradesh. Why? People go to Darjeeling, right? People go to Assam because they want to spend their vacations. Now, whether the people will go or people will not go to depends upon many factors. Their family income, size of the household, age of the head of the family member. It depends upon number of factors. They are your X1, X2, Xk, right? So here is, if people go to the resort visit, I'm writing 1. If they don't go to the resort visit, I'm writing 2. That is your dependent variable. If they are going to the resort visit, 1 means yes. If they are not going to the resort visit, 2. So that is your dependent variable. Now it depends upon number 1, annual family income. What is the annual family income of that? So obviously going to a resort visit will depend upon the income, right? So this is the income in thousands of dollars. Then attitudes towards travel. Even some of the people, they are having very good money, but they don't want to travel. So attitude is also very, very important. A person like me is fond of traveling. I used to go everywhere. This Saturday I'm going to Srinagar. Even last month I was in Srinagar. But wherever the opportunity, I always go. So that is attitude towards travel. Some people, they don't want to go. That's all. So if they have high attitude, so it's measured on 7-point scale, 9-point scale. So 8, 5, 6, they have given this thing. Then importance attached to the family vacation. How important? Whether vacations you will go or not. Again measured on a 9-point scale. Then household size. Small size, obviously income will be less. Large household, income will be high. So household size. Then also age of the head of the household. How much is the age? In both the groups, those who are opting for resort visit, those who are not opting for resort visit. I will not use this last one. So basically this is what the data is. This is your dependent variable, which is Y. And Y depends upon X1, X2, X3, X4, X5. So these are your X1, X5 variables. And these are your dependent variable. Now what I want, that out of these 5, how many can discriminate whether the person will go for a resort visit or not to go for a resort visit? You follow the data or not? Yes, please.
Yes,
Is the data clear?
Yes, sir.
yes,
Yes, sir.
Now, same type of example you can have, bank people. They use the discriminant analysis. Let me tell you how they use it. They issue credit cards and people purchases through credit card, and some people make payments in time, some they don't, and sometimes they forget about this thing. So those who forget about, they don't make the payment, are known as defaulters, and those who make the payment are known defaulters. So let's say your one category is defaulters, another category is known defaulters. So if they are known defaulter 1, defaulter 2, and now how they issue credit card. They ask you certain things like what is your income, last 3 months salary or 6 months salary slip, how on what position you are working, how many years of experience you have in this particular job, whether you have permanent residency or not. So there are so many parameters. And what is your credit risk? What is your credit ratio? So all these these things they measure. And based on that, they develop equation. And they develop equation. And in that equation, when a new customer comes and he asks for that I want to have a credit card, then they put all these parameters, their income, number of years of experience, where they work and all this, and they get discriminant score. And discriminant score, there are two centroids. One is defaulter, another is non-defaulter. If their discriminant score is closer to the non-defaulter, so they will issue the credit card. If their score is closer to the defaulter, they will refuse it. No, you cannot, sorry. Right? So this can be used in number of situations. You follow my point? Yes, please.
Yes, sir.
Okay. Similarly, how this discriminant analysis problem arises, it arises in 1934. And the discriminant function was developed by a scientist whose name was Fisher's. That's why this is called Fisher's discriminant function. Now, what happens actually? He came to India, and in India, in Madhya Pradesh area, some skulls, those who have been killed by the British people, they were found out. There were more than 100 skulls, right? And they were there for the last maybe 50, 60 years, and people were curious to know that whether it is a male skull or it is a female skull, because it's a skull now. Now, how to discriminate whether it is a male skull or a female skull? Then the Fisher pointed out that as far as he consulted the anthropologist, that there are certain bones in the head, and these bones can discriminate between male and female. Basically, there are 15 bones, X1, X2, X15. So they, for each and every skull, they have carried out the measurements, right? And they don't know whether it is a male skull or female skull in that particular area, because this is what the presumption was, that these skulls basically belong to this nearby area only. People die every day. And then whether a person is a male or female, you will come to know from the hospitals. And they have taken a huge amount of data of around 2,000 people, and based on whether a person is male, female, and they're all skull, 15 measurements of their skulls, and developed this discriminant function. They have developed a discriminant function. And then centroid were also known that this is male centroid, this is female. Now, these unknown skulls are there. They pick up one skull, note down their 15 measurements, put into that equation. They got the discriminant score. If their discriminant score was closer to the male centroid, then say that it is a male skull. Otherwise, it is a female skull. So that from there, this discriminant function emerges. So that was the pioneer work done by Fishers in 1934. So the story was important, right? How to discriminate or how to assign a new individual to a group. So I think the data is clear. Let's go for the analysis, how to conduct this discriminant analysis. So I have given you enough examples. What is the meaning of discriminant analysis? Very useful technique. And these days, you must have heard in the newspaper, there are certain skulls which are there in Anjala. Anjala near Amritsar. People have been killed by British people about 200 years back. And the research is there with the Punjab University, Chandigarh. And some people from anthropology and myself, we are involved with that kind of research. We are trying to find out. But that is not male and female only. We are trying to find out their ancestors. Some people claim that their ancestors were killed during that time. And now we are trying to match their DNAs, right? So this is what type of research we are conducting into. But anyhow, so let's go into discriminant analysis. practical application. Let me take up some data set. It's the same data set which we have resort visit or not to resort visit. What is this? It's getting the data. Okay. Oh, sorry. This data is something else, but anyhow, let me open that data which you are familiar with. Open that data. This one. Okay. All right. So it's the same data. People, if they are opting for resort visit, yes. If they are not opting, then it is no. So it is 1 and 0, I think. 1 and 2. 1 and 2. So that's a dichotomous variable. Then it depends upon family income, attitude toward travel, family vacation, household size, age of the other. This is I'm not taking. So these are the 5. 1, 2, 3, 4, 5. I want to discriminate. Which are the variables which are important to discriminate whether a person will go to the resort visit or not to go to resort visit. Okay. So here is, as I mentioned, that it is a classification technique. It is not a prediction technique. And people get confused between classification and prediction. Discriminant analysis is a classification technique, not a prediction technique. So go to classify. Cluster analysis is also a classification technique, not a prediction technique. So go to classify, go to hierarchical clustering. Sorry, not clustering, discriminant analysis. So this is discriminant. It says which one is your grouping variable. Our grouping variable is which can resort visit or not the resort visit. So this is your grouping variable. It says defined range. Defined range means because there could be 3 groups also. So range will be 1 to 3. So our range is 1 to 2. So minimum value is 1, maximum value is 2. If there are 3 groups, you can write 1 to 3 range. Then what are the independent variables? These 5 are independent variables. This one, family income, attitude toward travel, and all this. These are all, except this one. Okay. Now you have feed your data. Now what do you want to compute? Go to statistics. So you click on to means, univariate ANOVA. Univariate ANOVA will give you idea which variable can discriminate, which was not. Then you also look at within group matrices correlation. Then Fisher's discriminant function, standardized, and this is unstandardized. Standardized function will give you that which variable is the most important to discriminate, which one is the next one, which one is the next one, and so on. Okay, so this is what you need to click in discriminant analysis. Continue. Go to classify, and in classify you must click on to summary table and leave one out, classification. So these 2 are important, other things are not important. Continue. Save. Predicted group membership, discriminant score. So you can get discriminant score of each and every person. Probabilities of group membership. But we don't want to save. Only thing is we want to know the accuracy of the model. If you want, you can get it. For example, if I click on to predicted group membership, it will give you the result. Continue. That's all. So this is how to perform the discriminant analysis. It is done and you will get the results, and I'll show you the output. So this is here. It's running. So 30 observations data, 15 of them, they belong to those who have opted for resort visit, 15 those who have not opted for. This is just a mean and standard deviation table. 15 those who have opted for, and 15 those who have not opted for, total is 30. This is called basically the test of equality of group means, and this will give you some idea which variable can discriminate or important to discriminate and which ones are not, based on the ANOVA results, F value and P value. So let's look at the first variable, annual family income. Annual family income P value is 0.000. That means it is significant. So this is the variable which can discriminate those who will go for resort visit, those who will not go for resort visit, because it is coming out to be significant. Its P value is less than 0.05. Look at attitudes towards travel. It is non-significant, so it doesn't matter. Attitude doesn't matter much. Then importance attached to the family vacations. It is significant. So importance attached to the family vacation is significant, right? Then household size is significant, but age of the household non-significant. It doesn't matter. So out of the 5, at least 3 of them are significant. Which one? Annual family income, importance attached to the family, household size, right? So that is, these 3 are important to discriminate. Other 2 may not be. Other 2 may not be. Okay. Then this is a correlation matrix. Correlation matrix. Remember, if you have learned factor analysis technique is applicable when the variables are correlated among themselves. Let me just repeat. Factor analysis technique is applicable when the variables are correlated among themselves. And discriminant analysis technique is applicable when variables are not correlated among themselves. So here you can see very, very poor correlations. 0.195, 0.088, 0.012, 0.069, 0.012, 0.043, and so on. So very, very poor correlation. That means very important. If all these are correlated, then they cannot discriminate then if they are correlated. Now, as I mentioned, that canonical correlation has to be high. It lies between 0 and 1. So you can see it's 0.8, which is closer to 1. And the eigenvalue is also equally good. It's large, 1.7, more than 1. So that means model seems to be okay. And Wilks lambda value has to be significant. This is significant. If this is non-significant, let me just explain you. If this becomes non-significant, do not apply. For example, if your correlations are very high, variables are correlated among themselves, in that case, you can simply see that Wilks lambda will come out to be non-significant. And if it comes out to be non-significant, that means your variables cannot discriminate between the categories. That is the meaning, right? And this is the standardized canonical discriminant function. Standardized canonical discriminant function will give you the idea that which variable is most important to discriminate. For example, it says highest weight is with income, 0.74. So this is the most important variable. Next important is household size. That is the next one. Next is importance attached to the family. And then age of the household. And the least is attitude toward travel. So you can look at this size. The more the size, better. So this standardized coefficients will give you that which variable is most discriminant. And here is and structural matrix will also give you the same kind of interpretation. But advantage of structural matrix is it will be placed in order. You have to pick up that this is at number 1, this is at number 2. If there are 50 of this, then it is difficult to pick up. That's why people use structure matrix. In structure matrix, you will get the clear picture in hierarchical order. For example, annual family income at number 1, household size number 2, importance attached number 3. This is number 4 and number 5, right? So, okay. Then from where you can get the discriminant score, this is the equation to get the discriminant score. right? So if you double click here, you will get the discriminant score equation. So your discriminant score equation will look like this, that DS is equal to your constant. Constant is 0 point, this is minus, sorry. Minus point, this is constant, beta naught, minus 8.017 plus, then you start multiplying this, 0.084, multiply with income. Let me just write down I. I stands for income, just to save time. Plus, the second one is 0.059, multiply with the attitude towards travel. Let me put this as only travel. Then plus, I'm just writing the final equation, 0.120, multiply with importance attached to family vacation. Let me put this as V, plus the last two, household size, and that is 0.425, multiply this with household size, HS household size, plus the last one is age of the head of the household, 0.025, multiply with age. So this is how the equation will look like. So this is our discriminant equation, right? DS is equal to, it should be equal to, anyhow. So this is the equation, and from here you are getting these centroid. So if people are going for the resort visit, this is the value of C1, this is the value of C2. Now, if some new individual have come, you substitute, look at his age, his household size, then vacation and all this, substitute, you will get DS. If DS is positive, he will go for the resort visit. If DS is coming out to be negative, he will not go for the resort visit. And based on our data, this discriminant score, it has given you a prediction matrix, classification matrix, that out of the 15, those who have opted for the resort visit, how many are based on this discriminant function, how many have been correctly classified? It says those who were not going for resort, all the 15 have been correctly classified. But out of this, 3 have been misclassified. They have to be under yes, no under no. But here, under yes, only 12. Under no, 15. Right? So, how many are correctly classified? 12 plus 15, those who are along the diagonal. 12 plus 15 is 27. So, 27 divided by 30 multiplied by 100. That will give you 90%. So, 90% of the original cases have been correctly classified. So, as I mentioned, that if this prediction is only 30-40%, do not apply discriminant analysis. That model is not good. It has to be more than 70%. So that is this entire discriminant analysis procedure. Yes, please. If you have any question in discriminant analysis, I have explained you with the help of data. If you have any question, query, you are most welcome to ask. Yes, please. Any question?
So kindly show the first step to perform this statistics in SPSS.
Discriminant analysis?
Yes, this discriminant analysis.
Okay, let me do it again. It won't take. Now, interpretation is okay, right?
First step, sir.
Interpretation is okay?
Yes, sir.
Okay. So let me close this file. I'll just run it again for you. Just wait. So go to analysis. I'm just repeating the steps. Go to analysis. Go to classify. Go to discriminant. And substitute your group variable here. Our group variable was the resort visit. And your independent variables were these: income, attitude, vocation, household size, age. So all these are here. And income, attitude, importance, household size, age. They are all independent variables. Then in statistics, what you need to click? Means. univariate ANOVA, within group correlation, Fisher's discriminant function, standardized and unstandardized both. Because standardized will give you the idea which factor is most important. Continue. Then in classify, just look at the summary table, will give you how many cases have been correctly classified and leave one out classification. And in save, whether you save or not, I predicted the save membership, doesn't matter, right? You may not require this thing. So here it is asking that you have to give the range. So our range was 1 to 2. Continue. That's all. So you press OK and you are getting the same results. So that's the same result which I explained you in detail. Yes, please. Is that okay?
Okay, sir. Thank you.
Yeah. So
Sorry, last table.
there is cross validation.
Yeah, what is this?
Yeah, cross validation is checked according to the, it will leave one out. This is because I clicked on to leave one out classification, right? So what it has done actually, it has just left the one observation, computed the score. Then again in the second case, the second observation was deleted, again going for discriminant analysis. Then in the third was deleted, and that is called cross validation or leave one out. Leave one out technique is generally used for cross classification. Cross classification means if you leave some of these variables, some of these, then how much is your correctly classified score? So it says that if you apply cross validation, then out of the, how many have been correctly classified? 11 plus 13. 11 plus 13 is 24. So 24 divided by 30, multiply by 100, it comes to 80. So it says 80% are 80% cross validated score. What does this mean? Because this is based on your data. But if you go through the entire population, then at least in 80% of the cases, your validation is going to be correct. This is for your data, 90% for your data. But if you look at the entire population, then your prediction will be almost 80% correct. That is the idea of computing cross validated group classification. Yes, please. Is that okay?
Yes, okay.
Yeah. Any other thing?